So, for the fourth problem, we're going to be looking at this cylinder problem where the top of the cylinder is going to have a 5, 0. The bottom is going to have a outwards flux of -1. The side of this is going to be L, and it's going to have a phi d phi dr of 0. And then our dimension is going to be, let's do r, z, and then theta. Yeah, let's do theta. Or let's do phi. So now that we have this problem set up, let's do the boundary value problem. All right, so what is the boundary value problem here? Well, we can notice that over here this is 0, right? And over here this is not equal to 0. What we do have, though, is that this is going to be equal to 0. And remember how before I was talking about there's the Dirichlet and the Neumann, where this is the value and then this is the derivative. Well, there's actually one more, which is the Robin, which is going to be like something like C1 times theta, or phi, plus C2 times phi equals 0. So over here we actually run into this case. And this is what we'll be trying to solve for. So the second question asks, let's just call this 4a. Which direction has the homogeneous boundary condition? Well, we notice that this dr is always going to have a component that's equal to 0, but z is not. And of course, like, we don't have anything related to the actual angle. So therefore, from here, we can conclude that the r direction is homogeneous. And non-homogeneous is the z. Next, we use separation of variables to solve the PDE, and we can therefore develop a series representation of the solution. So we basically want to, again, solve the Laplacian as before, but this time in cylindrical coordinates. And we also know that the Laplacian here is dependent only on theta, or not theta. It's not dependent on theta. It's only dependent on r and z. So then therefore we know that we can set this equal to something like, let's just call this r of r and z of z. It's usually common practice to just make the function the capital letter of the variable you're solving for, just so that it's easy to follow. All right, we also know that the cylindrical form of this, so this is from, if you just look online, you can also derive this, but it takes a while. So usually I just look online, especially on Wikipedia. So I'll write this down. So Wikipedia, there is a thing called, I believe, um, del in cylindrical and spherical coordinates. And you probably also have the notes in class. So I use this page a lot when I was studying in the past. And essentially, it just gives you all of the direct solutions in the different coordinate spaces. So over here, you will be directly getting this form. Equals 0. And now we just follow the similar step to the first problem we did and just plug in our equation here and directly try to separate them. So let's just plug it in, and then we will be getting 1 over r d dr r dr dr big R plus 1 over z d squared z dz squared equals 0. And then we can rearrange them again. And with the side that we want to be, the side that's homogeneous is going to be equal to the negative squared. Since it's going to somehow be related to sine, cosine. But in this case, this is going to be another thing. So we are going to be doing here, we are z. So what we have here is a little bit different than what we did before with sine and cosine, and this is because we don't have a simple ODE that we're looking for. Let's try to expand this out a bit and just see kind of what this becomes. So we have this equals negative, but then this also actually equals let's see, r d squared r, oops, dr squared plus dr here. And from here, we notice that we can actually rearrange this a little bit. And we actually get what seems to be the Bessel equation. Which kind of makes sense because we're dealing now in more circular coordinates. But over here, we do need to do a little bit of modification. So we just multiply everything by r. Yeah. And we get the equation that we're looking for. So this is going to be Bessel of 0th order. And from here, we just plug in then what we already know. So we're solving here in terms of r. And this is going to be a of j and the r. And a is going to be a constant, and plus b of y lambda r. So this is going to all just be the constants we're going to be solving for. So from what we know about the Bessel function and how it works, since as small r, or just the radius, is at 0, then b has to also be 0. So the fact that just smaller is going to go to 0, then b equals 0, then that this assumption usually holds for a lot of cases. Then we can basically just get that our problem is a of j, and there's no y term. So all we have to figure out now is what happens at r equals 1, which is going to be the edge of the cylinder. Well, r equals 1, remember, is what happened when we defined r plus dr equals 0. So from here, we know that as r is going to be a j of this, then it's actually going to also be j of 0 times lambda minus lambda j of 1 times lambda. And this is going to be our set of solutions. And why is this? Well, this is just because of the property of the Bessel function, which is that if you have any derivative of the j component, then the derivative is going to lead to the next term for 1. So derivative of j1 is going to be equal to the negative of j1 of the same thing. So you could just simply plug that in here, and then you will get what you need. All right, so then now from here we have j lambda, and let's just call this k, which is equivalent to what we had as n before, and that minus lambda equals 0 for k equals 1, 2, whatever. And we find that this function can be determined actually directly just by solving for, or not this function, we can determine the other function, over here, by solving it the really traditional way that we did before, which was the hyperbolic method. And you could just simply plug this and get c sine h, or sinh lambda k plus d cos h lambda k. So here's like the other solution. And now we can just, let's try to just plot this out. So let's plot this part out first, because we already know what this one's gonna be. And what you'll see is that if you plot this, you'll have a oscillation that kind of grows. Oops, this looks kind of bad. And now we also do have some boundary conditions for z. So if you go back up here, it's going to be 0 at the height L, and it's going to be -1, or at least the derivative is going to be -1 for the height of 0. So let's go back down here, and we have z or let's just say c sine h of this is going to be equal to negative d cos this L. And that's just because at L it's going to equal to 0, and from here we can have the two equations that we need to solve for, and we just plug it in. So finally, yeah, our last equation, just after plugging everything in to both what we want, we basically just get z of z is going to be equals to negative c cos lambda kl sinh lambda k l minus z. And now you can simply put everything from here back together with what you saw from above to get the equation, which is phi is going to equal to infinity, k equals 1, ak, and then the Bessel, and times sinh where the constants are going to be determined. So finally, we can just apply the boundary condition to get the orthogonality conditions to find what A is, like last time. And this will just be done like how we always do it. So one thing to note is that for Bessel function orthogonality, we want to look at specifically, we need to include this r term. So it's going to be j, r times j, and then times another j. Like this one's going to be something like k, this one's going to be m. So applying this to here, what we're going to be getting is integral of r j lambda k r dr equals to ak lambda k integral from 0 to r 1 times r, and then j0 lambda r squared dr, and then times before what we had the gosh, actually let's move this to the side so it doesn't get in the way. And here is going to be the equation. And then from here, then you do your typical division times 2, and you are going to be left with a equals 2 over, and then use the Bessel function. You'll get here plus 1 times j1 lambda k cosine h of L. And that is going to be the solution. You may be asking how we arrived at here directly from here, so I'm gonna quickly talk about this. So basically what we have is that we have let's just start from this equation here. So we start with we start with knowing that this weight times j lambda k of r dr is going to equal to this a k cosh of this times 0 to 1 r j lambda k r squared dr. And this is just because we are simply multiplying the basis by the full set of functions, right? Basically the full solution. And we know that this actually, yeah, let's move a step before this first and say why this is. So this is because first you know that, okay, we want to start with the assumption that one, like all of our summation is going to equal to 1. Oops. And since we know that this is going to equal to 1, then the orthogonality means that this, with the wing function, right, this is Bessel, times 1 times our basis is going to be equal to this times our whole like thingy times the basis. So that's how we actually arrive at this solution. Okay, so let's move down now, and we have now that this is going to be equal to actually we already have this. Okay, so now we just want to evaluate the integrals and actually solve for this relationship, which will hopefully lead us to this. So to get that, what we want to do is first let's do the left-hand integral. And doing the left-hand integral, you'll directly get that this is equal to j1 of lambda k over lambda k. And why is this? Well, we know that the identity for this Bessel function is, or we should know, that its dr is going to be equal to the same as rp for whatever value it is going to be equal to same thing as this. So this is essentially basically just saying that when we take the derivative of Bessel function, we just get the index minus 1. So if we take the integral of this, then we'll get the index times 1. And we also notice that over here, this is p minus 1, right? So this is actually, this r is going to be, or this p is going to be the p from above. It is a bit more complicated if you want to go the full route and actually solve it. But essentially what it lands us at is here. Alright, now to solve the right-hand side. Well, then the right-hand side is essentially the same. And what you're going to be getting basically is, let's split this into the right-hand side, is going to be RHS, where RHS is 0 to a, and it's going to be whatever that we did before. E equals r squared. Oops. And that's going to be the same as this. So over here, our radius is 1, and the order that we have is p, which is 0. So p equals 0, r equals 1. So then we just simply plug in to plug those values in, and then we will actually just get 1/2 of j0 lambda k squared plus 1 minus 0 squared over lambda squared k, which is equal to 0. So you can remove that. j0 lambda k squared. And then since j0 prime is equal to j negative j1 from our identity table, then we can just simply rewrite this as 1/2 1 plus 1 over the squared j0 lambda squared. And finally, we get 0 to 1 r times j0 and k of r squared, and it equals 1/2 of 1 plus whatever we had above. Actually, j1. So finally, we just have to take these two steps and combine them. So this is going to be specifically this integral term. And we just combine it, rearrange it, and we will finally get the AK that we want.